Okay, let's continue. Our next speaker is Senya Shlosman, pedestal polynomial matrices with polynomial eigenvalues. Please.
Thank you. Um, so I see that this talk has several things in common with just the previous one. So I also want to say something about what that has to do with Igor Krichever. So unfortunately, not that much, but he was very happy with the list of authors because at the moment that the paper was written, Will Sawin was in Columbia, and I was still in Skoltech, and he was saying that he is a good addition to our team of authors, and by now he moved to Princeton, right? I mean, Will Sawin. Yes. So so I will also I will have some operators in my talk, but those are not commuting operators. So this is not the Igor has not much to do with well, he is not famous for that. But being the oldest participant in this room, I believe, uh, I decided that I say just few words about Igor because it turns out that I know him more than half a century. Half a century. That's strange to think about, even such numbers. So, so this is me and him in our first boat trip, which was during our students' year, and and this is we are sitting at military training in 1971. So this is him, this is Igor, this is Borya Dubrovin, and this is me here. And we had many boat trips with him. This is some intermediate one. He's with Natasha, his wife. That next one is our last trip, which is about 5 years ago. We are doing some topology here, as you see, trying to figure out what to do with this thing here. And this is the last picture is Serge Novikov with his friends and colleagues. As you see here is Igor standing here. This is Serge Novikov. This is our chairman, right? And this is again Borya Dubrovin. This is Victor Buchstaber and others. Okay, so Serge Novikov also passed away this month, as some of you know. So okay, this is now I pass to the topic of my talk. So this is that was just what all that had to do with Igor Krichever. So this talk is mainly about combinatorics of diagrams, of three-dimensional diagrams, plane partitions, and generating functions. So I will go slowly and with details so you can ask questions if something will not be clear. So I start with reminding you what Young diagram is. You just take the number k and you write it down as a sum of non-increasing integers. So the pi of 1 is the biggest one, and then the last one might be several of the last one might be 0. So this is a partition of the number of k, and schematically it can be drawn in such a way. So it is such a staircase, and so we have here we have totally 21 boxes in that partition. And then what one likes to know is the generating function, as we heard in the last talk. So this is you want to know how many partitions of of, of area of total area k is there, and then you write down the generating function for that sequence. It turns out that this generating function is given by this product of 1 over 1 minus t to the L. L runs from 1 to n. And this is easy to see, in fact. So if you indeed expand this product, this is the This is the product of those series. And then how you establish this one-to-one correspondence between the terms here and the diagrams. For example, in this one, see you have two rows of length 1. So you go to that product, and then you take from that sum the second term, t to the 2. That means you have two rows of length 1. Then you have no rows of the length 2. So from the second term you take just 1 here. Then you go back and you see how many lines of length 3 you have. Again, you have 2. So you go and you take from that product, oops, I go wrong way. From that product, you take the term t6, t to the 6, and this is the one-to-one correspondence between partitions and terms of that product. Okay, so this is all well known. So I just this is a reminder, and then you want to talk about plane partitions or two-dimensional analogs of those pictures. For example, you take a rectangle 2 by 3 here, and then you put boxes like that. So those are the boxes of the same height as before. So you arrange them in such a way that the heights decrease to the right and to the front. And again, you want to count how many of those are there. And this is again a famous question, and it has a famous answer. This is given by the Mahon formula. And so this is again a product over this rectangle, NYM. And here we have 1 over 1 minus t to the power L plus S minus 1. And this power is just, is known as the Hooke length of the cell LS. So you draw this rectangle, you put a point with coordinates L and S, and the area of that hook is what is appearing in this formula here. Good, and evidently there is a natural map from the set of all those plane diagrams to the usual Young diagrams. You just list all the columns of your skyscraper in decreasing order, and then you have a map from this set of all plane partitions to the set of Young diagrams with n times m entries. And okay, would be nice to have sort of an inverse map to that, but unfortunately the preimages of the various diagrams have different number of the number of preimages is different depending on the diagram, so it might be tricky, but now I want to explain in which sense one can do something like that. Namely, what one should do is to
space is closely related to hexagonal tilings. So when we look at a picture when some cubes are put together, it's related to some two-dimensional picture. And whenever we have tilings of squares or cubes of higher dimensions, it should be related to two n-gons and the ways of gluing and zonotopes and so on. So I'm asking whether there are some group actions and some topology on the Young diagrams, Young tableau, and their higher dimensions.
I have to say that I totally agree with what you said initially, and I will not comment on the second half because that would take me for too long. So I want to discuss still the relation between those two sets, and the relation. To explain the relation, I have to introduce those pedestals, which is a main object of my talk today, the main character of this story. So to explain what that is, let us take this rectangle n times n, and let us fix some linear order on it, which, for example, the one which on the top, that is one possible option. This is the other possible option, and then what we do. So imagine we have two different linear orders on this rectangle, and then we want to consider. Then we define what is a disagreement between those two linear orders. So we call a node a disagreement node if the order, the two nodes appearing under P and under Q, those are reversed orders. Then we call this a disagreement node. And for example, on that picture, we have one single disagreement node, this one, because see, we proceed. So this is our P, and that is our Q, and we proceed over Q, and then we increase this way, we also increase that way. Here we go this way again. This is consistent with that third order till we get here. Here we go down, and there we go in the opposite way. So we have one conflict here, and then this is the only vertex that we have the conflict, so we mark it, and then we define what is the pedestal of this second order, which is down there, with respect to the first one. In the following way, there is this formula here, but let me just tell you what that is. So there is one disagreement here, this side, so we put a 1 here, and then on all further vertices we also put 1 till we get to a second descent, and then we starting from there we put 2 and 2 and 2 till the third place. Okay, and this is again is sort of a plane partition. So all those plane partitions that you get this way, we denote by Q with the index P and Q. Those are two orders that we use to define it. Okay, and then the fact is that there is a bijection between the set of all plane partitions, the set P sub Mn, and a direct product of all Young tableaux of length n times m, and the set of all those pedestals E with the subscript P. And this one-to-one correspondence is explained here. So what one should do is the following. So imagine I want to define it from right to left. So let me take a partition pi, and let me take a pedestal Q. Then the corresponding plane partition, which is on the left-hand side, which I want to build from this Young diagram and this pedestal, is the following. This pedestal has some running order here. This is Q. So you take your partition P sub k, and you put it along that order. So you have an order, and then you put the members of this partition along that path. This Young diagram you put along that path, and then you also have to add the pedestal of this. Say it again. So P is, in this formula, P is fixed. P is fixed. Then you define the set all pedestals of P, and then you take all diagrams. And to every diagram and every pedestal, you correspond a partition. So you take your partition, you put it along the order of Q. Q gives you an order on your rectangle. So you put those y's, the terms of this one, and you add this other plane partition. Sum of two plane partition is again a plane partition. So this is this is a new partition. The claim is that this is a one-to-one correspondence between the two. Okay, so, and in particular, so if we now consider the generating function of the pedestals, then this bijection that I just mentioned shows that there is a formula, another formula for the generating function of plane partitions, which is just the generating function of Young diagrams times the generating function or generating polynomial of all pedestals. So just this is another way of writing down the generating function of plane partitions. And what is nice about that formula is that you can do this not on just plane partitions, but on every partially ordered set. For example, you can talk about space partitions, and you get a formula for four-dimensional Young diagrams. And McMahon also wrote down such a formula, but unfortunately his formula is very nice, but nobody knows what it counts. But in this way, you can write down those formulas in any dimension. So in particular, if we compare those two formulas, the McMahon formula and the one I told you, we see that there is in this fraction, actually, there is fine cancellation. So this ratio actually turns out to be a polynomial, though it is not straightforwardly evident. Okay, so those are the pedestals, and now what one can do is the following. So let's take. So this is not a rectangle, but you can supplement it with number 6. Then those are all 6 possible orders on the 2x3 rectangle, and you then you can write down then you can form a matrix. This matrix is indexed by pairs of linear orders on your set. So there is 5x5 matrix. Good, and then you try to compute the eigenvalues of that matrix. And the miracle is that those eigenvalues are those polynomials here. So looks like a miracle that cries for explanation. We tried several of those matrices, several cases, and all the time the eigenvalues are given by this by some polynomials. So we wanted to understand why that is. So actually, this 5x5 matrix, but the sum of along every row is the same. So that's another eigenvalue. This one is a polynomial is just the sum of those monomials. So that is the case. So all 5 eigenvalues are polynomials like that. And so the driving question for us was to understand whether this is always true, and if yes, then why that is the case. And indeed, this is the case, and even more general fact is known. So instead, before what we did to every pedestal, this QPQ to this guy, we were corresponding just its volume, Q to the volume of that pedestal. But actually, you can associate to every pedestal a monomial of several variables. So this is how many floors that pedestal has of height 0. This is how many L1. It has L1 minus 1 cells with height 0, L2 minus L1 of height 1, and so on. And so you associate to every pedestal a whole monomial. And this q to the power, in that case, t to the power is just, if you put x1 to be 1, x2 to be t squared, then you get the previous formula. And It turns out that the sum of all those monomials over rows of such a matrix is the same. So it's in a sense it's a stochastic matrix, and then in fact one can do the same thing not only for plain partitions, but one can do this just for any partially ordered set, for every poset. And so one can consider again this matrix, which is this pedestal matrix. And the main result of this talk, which is obtained together with Richard Kenyon, Maxim Kontsevich, Oleg Ogievetsky, Cosmin Pohoata, Will Sawin, and myself, is that this matrix, all the eigenvalues of that matrix are again polynomials with integer coefficients. So this is surprising, right? Yeah. So this we were mesmerized by this for some years, but finally we have a proof of that fact. And so let me give you another example. Let us consider this partially ordered set with 6 elements. So it's just a Young diagram written there, drawn there. That one has 16 orders. So the matrix then is 16 by 16. So those monomials are monomials which would appear in that matrix. So for brevity, they are denoted by A1 to A10. So this is the matrix, 16 by 16. And then you compute the eigenvalues. And again, those are the eigenvalues here. So those are polynomials in those x variables. And the last line is just the sum of all, sum along the row of those a's, and others are sum with alternating coefficients. And this index here, that means that this value appears 3 times. Okay, so this is the theorem, and I want to explain the proof of it. And the proof is, well, there appears some objects which we were not initially counting on seeing. So the result, what we would show is that the matrix Mx, this matrix of pedestal matrix, can be written as a linear combination of some other operators, MFs with integer coefficients, and though they are not commuting, those MFs are not commuting, but anyway, one can do conjugation of a simultaneous conjugation of all those MFs in such a way that the resulting matrix would be upper triangular with integer entries on the diagonal. So this is, and that would imply our statement. So there are many. Okay, so that's how it goes. So let me try to explain what those MFs are. To explain that, I first tell you what is a filter of a partially ordered set. So if X is a partially ordered set, then you consider, then we consider a surjective map from X to segment of integers from 1 to k, which k is less than or equal to n. And then the only condition is that it respects the partial order. If we have a filter and it has B1 occupants on the first floor, B2 occupants on the second floor, and so on, then we denote in this way all the filters which have this restriction that the population on the level I of that filter has Bi occupants. Okay, and then if we have a filter F on X and the linear order on X, then we can build a new linear order, Q, which would depend on P and on F. And the construction is the following. If we take some floor of the filter F, it is all the values, all the points of X where F is taking some constant value, then we just put on that floor, we just keep this partial order P there. And if the elements A, alpha AI and alpha Ji in different floors, then we put the order, the same order as they are ordered according to that filter, F. So once we have a linear order P and the filter F, then we define a new linear order Q of F and P. And then we define this matrix, this MF, the matrices that we would enter the proof, and it is a definition. So the matrix MF, the matrix element, the matrix is indexed by two linear orders, and so the entry is 1 if the order Q is obtained from order P by action of that filter F, and it is 0 otherwise. Okay, and so those it turns out that those matrices, they form actually a semigroup. If we multiply them, you get again you have also a matrix which is again it corresponds to some other filter. So there is some structure on those filters, but it is easier to explain this geometrically. So this filter semigroup is better defined to be a phase semigroup. So I define some other semigroup, and then I will tell you that those are the same. So what is this phase semigroup? So we have n is our number of elements in the X. So what one should do is the following. One takes n-dimensional subspace, Rn, and one define what is called braid arrangement AN of hyperplanes in the space Rn by just considering all the hyperplanes Hij, which are defined like that, where the ith coordinate is coinciding with j's coordinate. And then if you take away the union of all those planes, you get a collection of cones, open cones, and each such component is called a chamber. And then if you take several chambers and the union is convex, then what you get would be, it is called a cone. So let D of n would be the set of all different possible cones defined by this braid arrangement of hyperplanes. Okay, now to every partially ordered set of n elements, one can define what the corresponding cone of that. Namely, you take all the half space Kij, which correspond to the relation I is less than or equal to j. You take those half space, and you then take all the intersection of all those half spaces, and then you get a cone because it's an intersection of half spaces. So to every partial order, you correspond a cone, and what turns out is that this correspondence is a one-to-one correspondence between all structures of all options of putting partial order on X and all cones that you can see in this hyperplane arrangement. And then when we understood that, we was a little bit puzzled, so we decided to check it. So we took the case when you have four different elements, like you see on my T-shirt. There are four individuals, so those four are different. And then you want to know how many partial orders you can put between them. So this is the intersection of this hyperplane arrangement A4. You should project it into R3, and then you intersect what you get with the unit sphere, and then you get such a nice picture. It almost looks like a Platonic body, except that those rectangles are not right rectangles. They have two angles are 60 degrees and one angle is 90 degrees. So there are 24 triangles which are partitioned in the sphere. And then you count how many convex sets you can get from those. So there are many ways you can do them. You can take the whole sphere, the hemisphere, a piece of it between two great circles, which are moons, and so on and so forth. You add all them, and then you find out the number 219. There are 219 different convex sets, and this is the same as the number of partial orders that you can put on 4 different individuals, distinguished individuals, as you can find in this list of sequences. You can find this number there. So after that, we were sure that this is a correct statement. And now there is, as I told you, there is a structure of semigroup on that, on those faces of this on this set of on that structure of hyperplanes and all faces of lower order. So there is this definition here. What is this product? But let me just explain it on the picture. Okay, maybe I use this other blackboard. So so this is analog of that picture for it in dimension 3. So we have here 6 chambers, 6 faces of the codimension 1, and 1 face of codimension 2. So the product is defined as follows. If I want to multiply this chamber with this face, for example, I choose a point here, I choose a point there, so I multiply this chamber, say F1, by this other chamber F2. So then F2 acting of F1 is defined as follows. You take a point here, you connect it with a segment here, and then you make a little bit a step back, so you get here. That belongs to some chamber. So this is F3. This is the one which corresponds to that point. That point belongs to that. This is the smallest chamber that contains that point. So this is your definition. So this is this phase product. This is a structure of this is a definition of the product, and that product has some properties. And for example, if F double prime is a chamber, then F double prime F prime equals to F prime. And again, if F prime is a chamber, then F prime of double prime is also a chamber. So the faces are acting on chambers here, and
I'm pretty sure that this should give rise to actions of great groups on young tableau of 5 dimensions. So when we switch from one situation to another situation, when we do some range arrangement,
it seems that this is not a question, I believe, right? So maybe you then say it later on. Thank you. Okay, so this product is associative. So this is indeed a semigroup, and it has certain properties. So F times F squared is F. So all those are projectors, and FGF equals to FG. And because of that, this semigroup is called left regular band. This is a name we learned after we found that. Okay, and then on that slide it is explained that the filters and the faces are just the same thing. You might just believe me, and then let us go further on. And this is and then one can understand what does it mean to have 2 filters, to multiply them. Well, you just read it out from the definition of the product of faces. Good, and then finally this object appears. This matrix M sub F is the following. You take a filter F, and you take a linear order, which is also a filter, and then you define the matrix MF with entries which are indexed by pairs of linear orders, the matrix element PQ is equal to 1 if the order Q is obtained from the order P by action of the filter F, and it is 0 otherwise. So those operators are important for the proof of the theorem I promised. And the remark is, again, as I told you, those are not commuting operators. And the fact of life is the following, that if we take our pedestal matrix Mx, and this is just, it is written as a sum of monomials times a matrix with entries zeros and ones, and then there comes a formula which is which is just exclusion inclusion formula here, and I don't want to explain this because but one stares for it for a few minutes and one see that indeed this is true decomposition of the objects that we are interested in over those matrices MFs for different Fs. So you see here there are different subsets of filters. So this is just exclusion inclusion formula, and I will not say much about it. But here it is written why it is true. So if you want to read this and then think about it, then probably the slides would be available. That's why this inclusion exclusion formula holds. Very good. So then from now on there is a straight way to do the conjugation that I promised, namely, so we have our matrices MFs. They are of the size of how many linear orders on X are there. Now let us throw away all the linear, or let us take X to be totally unordered set. So it has n factorial elements. I mean, if we don't have any partial order, then it has much more linear orders than initially it was. So and so now matrix M of X is a submatrix of M f X bar when we abandon all the orders. You look on it for a while, and then you see that this M f X is a block of the matrix M f X bar, a square block of it. So if the bigger matrix has all eigenvalues integers, whatever you want, then the smaller one also has the same. So you don't actually need the order on X. Without order, it is. So we prove more. We prove that the bigger matrix has all eigenvalues which are integers. And then we go to still bigger matrix, which is what you do. Before we were talking about, so now we put a very, very mild order. We take all the edges and we order every edge independently of each other. This is called tournament. So on every edge independently of each other, we put a relation bigger or equal. Very good. This is still bigger matrix. And again, the matrix we are interested in is a block of that bigger matrix. So why don't we study if this even bigger matrix? And again, filters are also acting on those tournaments in the same manner as it was acting on linear orders. So so we still have those matrices there as well. And then, so we have to study those matrices M sub F. F is a filter, and T is all possible tournaments on the set of n elements. Very good, but then the final remark is that this biggest matrix is actually a tensor product of 2 by 2 matrices, because the tournaments are so defined that on every edge you do it independently. So the matrix we're interested in is just a tensor product of 2 by 2 matrices, and therefore it's enough to check what we are going to prove just in the case n equals 2. So just one edge, and you consider all possible tournaments and filters there. So there are just 3 matrices here, which you see. And then you just check that each of those 3 can be conjugated by this matrix U, which is 1 over square root of 2, 1, 1, 1 minus 1. And then you do the 3 conjugations, and you see that all the diagonal elements are integers. That's the end of the proof. So you know the story that somebody came to a circus selling them the trick that a crocodile is playing piano and the monkey is singing. And everyone was very mesmerized by this, and they were asking, how you do this? And finally, the answer he gave after some time was that, you know what, of course, this is a lie. So monkey only opens its mouth. The crocodile is playing and singing. So this is how that proof works. So that's it. Thank you for your attention.
Thank you very much. Question, please. Question, comments? Yes, please.
Can you repeat how did you use discrete Fourier transform?
I cannot hear you even with the mic. Huh? Forget it. Just take this matrix. But they no, they are not. They are not.
Okay. Thank you very much. Thank you very much.
Thank you for your attention.